Hi everyone and welcome to NMC 1. Today we'll be looking at a class test from 2019. The first question, complete the table for A, B and C. So the family of materials for graphite. Graphite is a ceramic material. The class of materials for a steel is a ferrous alloy, and a bone is a composite. If you want to learn more about families of materials and class of materials and their uses as well, I would recommend that you download the CES Material EduPack software. I don't know if there is a free version online, but you must just check and find out. Let's go to the next question. Question 2. Consider the HCP structure shown below. 2A. Will there be the change in coordination number when 3 atoms in the center of the unit cell shown is removed? Give the coordination number before and after removal of the 3 atoms in the center. So you can redraw the HCP without the central atoms. Do it like this. So we have these atoms. And the center atoms, these are atoms on the base, on the face, but these atoms are the ones that are removed. Now they want to know if the coordination number is going to change. Yes, it's going to change. The reason it's going to change is because the stacking sequence is going to change. The stacking sequence which will result in a change in the coordination number, because the nearest touching atoms from a specific reference atom will not be the same. But they want to know the old coordination number and the new old coordination number before the removal. So for this one, you know that the cell at the top would have these 3 atoms. Now we can choose this reference atom and count the nearest touching atoms. It would be this 3 at the top, then 4, 5, 6, 7, 8, 9, and then the ones below 10, 11, and 12. So the coordination number will be 12. The new coordination number after the removal you know it's going to be at the top, will just be the subsequent atom, basal atom will touch this one. The surrounding atoms will also touch. So it's 1, 2, 3, 4, 5, 6, 7, and 8. So the coordination number for the new one would be 8. The following question 2b, if magnesium has the above ACP structure and has an atomic weight of 24.31 grams per mole, what would be the effective mass of the atoms in the unit cell? This is what we have here. We have the atomic mass, which is 24.31 grams per mole, and we know the theoretical density of any material is according to this equation. And we also know that density multiplied by volume is equals to mass, which in turn is equals to this. After rearranging of this equation, this is what you'll get. Now we can solve the problem. So the effective mass is equals to the total number of atoms. We have to count the total number of atoms. Let's quickly just write as a side note, you know that total number of atoms, effective number of atoms in HCP, we have 12 atoms with a contribution factor of a sixth. These are these atoms: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then you have 2 atoms contributing a half. These are the basal atoms, this one and the one at the top. And you have 3 full central atoms. They're in the middle of the cell. So that gives 6 atoms per cell. So we have 6 times 24.31 over Avogadro's number. It should give you 2.422 times 10 to the minus 22 grams. That's the effective mass. Let's move to the next question. This question 3.1, the diffusion coefficient of chromium in chromium oxide is 4 times 10 to the minus 15 centimeters squared per second at 727 degrees Celsius, and 1 times 10 to the minus 9 centimeters squared per second at 1400 degrees Celsius. Calculate D0 for the system. That's the pre-exponential. We know that the Arrhenius equation associated with diffusion is D0 exponential QD over RT. And the subsequent values, can call them DCR1. That's 4 times 10 to the minus 15 centimeters squared per second. And DCR2 is 1 times 10 to the minus 9 centimeters squared per second. This one is at 727 degrees Celsius, which in kelvins, 727 plus 2, that's 1,000 kelvins. And this one is at 1400 degrees Celsius. In kelvins, this is 1673 kelvins. Now we want to solve for D0. So we'll create a simultaneous equation computation. So we'll have to learn both sides of each of those equations. We'll have a len DCR1, which is equals to the len D0 minus QD. The reason for that is because when you len an exp, an exponential value, the len and the exponential value cancels out, and you have the subsequent values of the exponential. One over RT1. This will be our first equation. And our second equation will be the len DCR2 equals to the len D0 minus QD 1 over RT2. It's our second equation. And if we further break down D2 to resolve for QD, we would have len DCR2 minus len D0 all over RT2. This is subsequently QD is equals to me make sure I'm not making any mistakes here. Actually, there's a mistake here. Let's scratch out this entire part of the equation. Oh, you read it just now. This is what it should be. Should be RT2 len D0 minus len DCR2. Let's call that 3. And let's put 3 into 1. That way, the only unknown that we'll have is D0, which is our pre-exponential. So you'll have the len DCR1 is equals to len D0 minus, all in brackets you have len D0 len DCR2 all in brackets will be multiplied by RT2 times RT1. And if you resolve this, these two will cancel out. The R values will cancel out. Cancel each other out. And when you put in the temperatures, you'd have len D CR1. I'm putting the temperatures first so that it doesn't create any confusion. Is equals to len D0 minus len D0 minus len DCR2 this would be multiplied by T2, which is 1673, which is also multiplied by 1 over 1000 kelvins. And once you've been able to place all the subsequent values, and you solve for D0, I'm just gonna cut to the chase here because this is the answer you should be getting. There's a very lengthy answer and the space given here is very limited, so I'm just gonna cut to the chase. You're just gonna be solving for the value of D0. 0. So in this equation, you put 3 into 1 minus len D0 minus len D CR2 all in brackets. You have len D0 minus len DCR1 all in brackets minus len D0 minus len DCR2 all in brackets. You have len D0 minus len DCR1 all in brackets minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 minus len DCR2 all in brackets minus len D0 min the length of DCR1, you put the diffusion coefficient here, and you put the diffusion coefficient there. You place the temperatures, and you solve for the ln of D0, and this is what you should be getting. You're welcome to make any inquiries with regards to this question. Never you don't understand, but from where I am, I think that you're familiar with the simultaneous equations. That's the only complex, so to speak, thing that you'll encounter in the equation, as long as you understand what they are asking of you. So let's move on to the next question. 3.2, determine the value of D at temperature of 679 degrees Celsius with the aid of figure 2. So I want to determine the value of D. What's the value of D at 679 degrees Celsius, which is subsequently 952 kelvins. So now here we want to read the x-axis first. Would have to rearrange because it's the x-axis, it's 1000 over the temperature in kelvins. So you'd have 1000 over 952. This is equals to 1.0504. So you know your x-axis value, the value that you're gonna read on the scale. Read off the value. I won't be precise when I'm doing it. I'm just gonna do it hypothetically. And you'll go up here and read the subsequent value of D here. But remember, this is a logarithmic calibration. So what you'll do is you'll count the number of Y calibrations. So now in this instance, you have our values somewhere between 10 to the minus 12 and 10 to the 10 to the minus 10. So our value is somewhere here. So you count the number of calibrations of Y, all of them, all the way from 10 to the minus 10 to 10 to the minus 12 using your ruler. You would get 20 calibrations, and the calibrations from X from 10 to the minus 10 to where the reading is, your X value here, let me just write it down here, is 11. So to know what the value is, you'd say 10 to the minus 10 plus X over Y. This would be 10 to the minus 10 plus 11 over 20, which is subsequently 10 to the minus 10.55 meters squared per second. If this is with regards to the units being in meters per second, they haven't told us what the units are in, so We'll just assume that it's in meters per second. Let's move on to the next question. Question 4. A material has an ASTM grain size number of 6. ASTM grain size number of 6. It is grain size number, not grain size. Grain size number. Pay attention to this. 24 grains. 24 grains are observed by a microscope at 200 magnification of 200 in a circle of unknown surface area. Calculate the diameter of the circle in centimeter. So they are looking for the diameter of the circle in centimeters. In centimeters, what is it? So what we know from the equation, the STM equation, that N is the number of grains per square inch. Magnification to the power of 2 of 2g to the power of g minus 1. And here we've been given our magnification as 200. That'll be over 100 squared 2, and we have g, which is 6. That would leave 4n is equals to 32. And what we know is that n, let me just write it on the side here, n is number of grains per inch squared, right? So that would mean that we have our n value is 8 grains per inch squared, right? But we've been tasked to find the diameter of the circle. So what we'll do is that we know that there are 24 grains. Right? And we know that we have 8 grains per inch squared, and all that is actually equivalent to our area, which is equals to pi r squared. And we know, let me take it to the top. We know that 1 inch is equals to 2.54 centimeters. But we'll come back to this. So according to that equation, 24 divided by 8 is 3. So we have 3 is equals to pi r squared. So 3 over pi to the power of a half is equals to our R value. And we know that 2R is equals to D, which is the diameter. And this is what we'll have. We'll have 2 times 3 over pi to the power of a half. Then our D value would be 1.954 inches. And subsequently, with the conversion, this would mean that therefore the diameter is 4.96 centimeters. This is approximately 5.0 centimeters. Hopefully this makes sense. Let's move on to the next question. Question 5. Calculate the diffusivity of carbon in 1022 type of steel. 0.2 weight percentage carbon of which a gear is made, which was carburized to 0.35 weight percentage of carbon at a depth of 0.8 millimeters below the surface in 8.07 hours at a temperature of 927 degrees Celsius. Let the surface concentration C be equal to 1.2 weight percentages. So let's write down every value that we have. C0 initially is 0.2 weight percent. The specific concentration at the given depth is 0.35 weight percent. The specific distance on depth is 0.8 millimeters, which is equals to 0.8 times 10 to the minus 3 meters. And we have the given time, which is 8.07 hours, which in turn is 29,052 seconds. And we have the temperature, which is at 927 degrees Celsius, which in kelvins is 1200 kelvins. And the surface concentration is given as 1.2 weight percent. Now we use the error function equation, Cx minus C0 over Cs minus C0 is equals to 1 minus the error function, which subsequently leads to this as well. And we know that Z is equals to X over 2 root dt. What that means is the error function can be written as error function of Z, because z is equals to what is inside the entire function. So we can substitute the values. We have 0.35 minus 0.2 over 1.2 minus 0.2, and we bring over the 1 minus the negative sign. We'll have an error function of z, right? And you find the error function value. Error function value is 0.85. You go to the error function table. Error function table. You find the corresponding values. The values above 0.85 for the error function is 1.0. The corresponding value of that is 0.8427. The error function value we got is 0.85, and the subsequent, actually it's the other way around. Let me check my error function table and see. It is the other way around. Sorry about that. The error function value that's above this is 0.8427. The corresponding z value is 1.0. The error function value that we got is 0.85, but we don't know the associated z value. The value below that on the error function table is 0.8802. Corresponding value is 1.1. So you do a correlation of what is on the right should be equal to what is on the left hand side in the same sequence. So you'd have 0.85 minus 0.8427. 0.85 corresponds with z1. 0.8427 corresponds with 1.0, and 0.8802 corresponds with 1.1, and 0.8427 also corresponds with 1.0. So you solve for z. Let me just fetch my calculator. The z value that I get is 1.0195, and we know that z is equals to x over 2 root dt. Subsequently, 1.0195 is equals to 0.8 times 10 to the minus 3 over 2 root d times T. The T value that we got is 29,052 seconds. So once you resolve and you find the value of D to be 5.2987 times 10 to the minus 12 meters squared per second. That's the diffusion coefficient value, which is representing the diffusivity of carbon in this particular steel. Well, that's it from me for this specific class test. I'll see you on the next video.